Section 2.6 discusses related rates. So what calculus allows us to do is take a known rate of change of one quantity and relate it to the rate of change of some other quantity. And up till now we really couldn't do that. Alright, so let's take a look at how that works and how calculus allows us to do that. So related rates is all about rates of change of two or more variables with respect to time. So these derivatives are all going to be with respect to time. Okay, so a good example, I think a kind of a simple example to start with is this idea of an expanding circle. So say we have some circle, it has a radius r, and that radius is increasing by 2 meters per second. Alright, so it's increasing quite rapidly. So we know that we could ask the question, how does the circumference change? How fast is the circumference changing if the radius is changing at 2 meters per second? So we know that the circumference is equal to 2 pi r. So that's how the quantities themselves are related. But we want to know how the rates are related. So in order to do that, we have to take the derivative of both sides with respect to time. So when we do that, we have the derivative of the circumference with respect to time equals 2 pi, and then the derivative of r is dr dt. You can see that we're taking the derivative implicitly here on both sides. And so what that means is if our radius is growing at 2 meters per second, then our circumference is growing 2 pi times that 2 meters per second. So our circumference is growing quite a bit faster. Right? That's a little bit different if we talk about how the area might be changing. Right? So we know the area is equal to pi r squared. So when we relate those quantities together, we have that equation there from geometry. Now again, we're going to take the derivative with respect to time of both sides. So we get dA dt equals 2 pi r dr dt. Alright, notice here that the rate of change of the area depends not only on how fast the radius is changing, but also what the radius currently is. You can see that the larger the radius is, even for a constant rate of change of radius, if I have a larger radius, the area is going to change by more. Right? And that's not necessarily an intuitive idea. Let's take a look at sort of maybe a thought experiment about why that might be the case. Imagine I have a circle with a fairly small radius, and I choose some unit to grow that radius. So I maybe if I kind of think of this as 1 unit here, I'm going to grow that radius. I'm going to expand that radius by another unit. And you can see that I've grown my area by this amount here. Right. Now look at a larger circle. So I have some radius, r. It's larger than the previous radius. And if I expand that circle by another 1 unit, now my circle is going to be this size. Alright, so in each case, I've expanded the radius by 1 unit. But you can see here that my area has grown considerably larger, by a considerably larger amount than it did when I expanded my radius by 1 unit on this smaller circle. So that gives you a little bit of an insight into why the rate of change of the area depends not only on how fast the radius is growing, but also the current size of the circle. And the larger the current size of the circle, in other words, the larger the current radius, the more area we're going to gain by expanding our radius by any amount or at any rate.